On November 8, 2025, a researcher at Auburn University in Alabama opened a set of telescope images on his screen and stopped. He had been expecting to see one comet, a routine observation, a backup target chosen at the last minute after the original comet became inaccessible due to a technical constraint. Not a glamorous assignment, not a high-priority observation, just a comet, just data. What he saw instead were 4 comets. Where there had been one object the day before, there were now 4 separate fragments, each surrounded by its own cloud of gas and dust, each moving independently, each the remnant of something that had existed as a single unified body for longer than the Earth has been a planet. The comet had broken apart. Not before the observation, not after, during. While the Hubble Space Telescope was pointed directly at it, capturing images across 3 consecutive days, the object had begun to tear itself apart. The researcher, John Noonan, described the moment simply: "We knew this was something really, really special." He was understating it considerably. What Hubble had just captured was something astronomers had been trying and failing to observe for decades. The death of a comet, not in aftermath, not in reconstruction, not from indirect evidence assembled weeks or months after the fact, but in real time, days after it began, while the telescope was still watching. And the story of how it happened, why it happened, and what the wreckage is now telling us about the oldest objects in the solar system is one of the most remarkable accidental discoveries in the history of observational astronomy. To understand why this matters, you first need to understand what comets are, and why catching one in the act of breaking apart is so extraordinarily difficult. Comets are among the oldest objects in the solar system. They formed more than 4.5 billion years ago in the cold outer reaches of the disk of gas and dust that surrounded the young sun before the planets had fully assembled. While the inner solar system was a violent place, rocky bodies crashing together and merging under gravity, building the terrestrial planets through catastrophic collision after catastrophic collision, the outer solar system was quieter and colder. The material there never gathered into a large planet. Instead, it remained as a vast population of small icy bodies, kilometers across, preserved in the cold darkness far from the sun's warmth. These are comets. Snowballs of ancient ice and rock and dust, formed from the same primordial material that built everything in the solar system, but never incorporated into a planet, drifting in the cold outer darkness for billions of years, occasionally perturbed by gravitational interactions with the giant planets and sent on long elliptical journeys that bring them plunging toward the inner solar system. When a comet approaches the sun, everything changes. The solar radiation heats the surface. The ice begins to sublime, converting directly from solid to gas without passing through liquid form. The escaping gas drags dust with it, forming the characteristic tail that stretches away from the sun. The comet that was invisible in the darkness of the outer solar system becomes temporarily brilliant. A glowing object visible across the inner solar system, and sometimes from Earth with the naked eye. But the heating that makes comets visible also destroys them. The same solar radiation that sublimates the ice creates thermal stress across the surface. The outgassing that produces the tail also carves channels and weaknesses through the interior. Comets that have made many previous passes of the sun accumulate damage, and comets making their closest approaches, passing inside the orbit of Mercury into the most intense solar heating they have ever experienced, sometimes do not survive. They break apart. The structural integrity of a body, held together by the gravity of a few kilometers of ice and rock, is not unlimited. When the thermal stress exceeds the tensile strength of the material, The comet fragments. This happens. We know it happens. We have known it happens for a long time. The problem is that we almost never see it happening. The reason we almost never catch a comet fragmenting in real time is a problem of timing that borders on the impossible. To catch a comet breaking apart rather than already broken, you need a telescope pointed at the right object at the right moment. But comets are numerous, and telescope time is precious, and the specific moment of fragmentation cannot be predicted in advance. A comet that appears structurally intact on Monday might be in 4 pieces by Thursday. If no telescope was pointed at it between Monday and Thursday, the fragmentation is missed. You find the 4 pieces later, and you reconstruct what happened from the evidence, but you do not see the moment itself. Astronomers had tried many times to solve this problem. The way you solve problems of timing in astronomy is by proposing dedicated observation campaigns, monitoring specific comets that appear to be at high risk of fragmentation. The attempt to catch a comet breaking apart in real time had never succeeded. Every fragmentation event that had been studied before had been studied in retrospect. The Hubble Space Telescope had been operating for over 35 years. In that entire time, across tens of thousands of individual observations of comets and other solar system objects, it had never caught a comet fragmenting this close to when it actually fell apart. And then, it happened by accident. The original target of the observation program was a different comet entirely. The research team, led by principal investigator Dennis Bodowitz of Auburn University in Alabama, had one time on Hubble to study a specific comet and its chemical composition using 2 of the telescope's most sophisticated spectrographs. This was legitimate, important science, the kind of detailed chemical analysis of cometary composition that reveals the raw ingredients of the early solar system. But technical constraints made the original comet inaccessible. Specific scheduling and pointing requirements that Hubble operations demand could not be met for that particular object at that particular time. The team had to find a substitute. They chose C/2025 K1 Atlas, not because it was special, not because it showed any particular sign of being about to fragment, not because of any scientific prediction or theoretical expectation. They chose it because it was accessible, and it was a comet, and they had telescope time to use. Hubble pointed at it on November 8, 2025. The telescope took images. The data came down. John Noonan opened it the following morning. 4 comets, where there had been one. The irony is now we're just studying a regular comet and it crumbles in front of our eyes. That was how Bodowitz described it. Regular. That is the word he chose. A regular comet, chosen as a backup target, coincidentally visited by a telescope at the precise moment it began to disintegrate. A moment that the entire field had been trying and failing to observe for decades. The probability of this alignment, the specific comet, the specific instrument, the specific 3-day window, arriving simultaneously at the moment of fragmentation, is what makes the discovery so extraordinary. It is not just scientifically significant, it is genuinely, statistically improbable in a way that makes it feel like something that should not have happened. What the images showed over the 3 consecutive days of observation, November 8th, 9th, and 10th of 2025, was the comet fragmenting in real time in a way no instrument had ever captured this close to when it actually fell apart. Before the observation began, K1 was a single object, probably around 5 miles across. A modest comet, not particularly large by the standards of long-period comets, but intact, coherent, a single body with a single trajectory and a single history stretching back 4.5 billion years to the formation of the solar system. By the time Hubble took its first image, K1 had already been breaking apart for 8 days. The team established this by working backwards from the positions and trajectories of the fragments, reconstructing the timeline of the fragmentation event. The breakup had begun 8 days before Hubble ever pointed at it. But 8 days after a comet begins to fragment is still extraordinarily early. Most fragmentation events are discovered weeks or months after the fact. 8 days after is close enough to the moment of breakup that the physical evidence of the event is still fresh, the fragments still close together, the history of the event still reconstructible from direct observation rather than inference. Hubble caught K1 fragmenting into at least 4 pieces. Each piece was surrounded by its own coma, the fuzzy envelope of gas and dust that surrounds a comet's icy nucleus as it sublimates in solar heat. Each piece was moving on a slightly different trajectory, the diverging paths of fragments that had recently been part of the same object. From ground-based telescopes, the fragments appeared as a barely distinguishable collection of blobs. From Hubble's orbital vantage point, above the distorting effects of Earth's atmosphere, they were cleanly resolved as separate objects. And then, during the observation period itself, as Hubble watched, one of the smaller fragments broke apart again. A fragment of a comet fragmented. The process of disintegration was still ongoing, still active, still producing new pieces from old ones in real time while the telescope was capturing images. Never before has Hubble caught a fragmenting comet this close to when it actually fell apart. That was Noonan's assessment. Most of the time, it's a few weeks to a month later. And in this case, we were able to see it just days after. But the real-time fragmentation imagery is only half of what makes this discovery significant, because the data Hubble collected in those 3 days contains something that nobody expected to find. Something that has opened a small but genuinely puzzling mystery about the physics of comet surfaces. When a comet fragments, the fresh ice inside the object is suddenly exposed to direct solar radiation for the first time. The ice that has been shielded by the outer surface for billions of years encounters the full intensity of sunlight. And when fresh ice sublimates under direct solar heating, it produces enormous outgassing events, sudden explosions of gas and dust that from Earth appear as dramatic brightenings, the comet suddenly becoming many times more luminous than it was before the fragmentation. This brightening should happen almost immediately after fragmentation. Fresh ice exposed to direct sunlight should sublime rapidly. The physics is straightforward. The model is well established, except it did not happen immediately. The team found a delay of 1 to 3 days between when the comet fragmented and when the brightening outbursts were seen from the ground. The fresh ice was exposed, the solar radiation was present, but the dramatic sublimation event was delayed by a day, by 2 days, by 3 days, inconsistently across different fragments. The team has a hypothesis. The most likely explanation is that a substantial dust layer forms rapidly on the exposed ice surface even after fragmentation, insulating the ice from direct solar heating and delaying the sublimation event until the dust layer itself is thick enough to be blown away by the pressure of the gas beneath it. But this is exactly the kind of process that has never been observed directly before, because nobody has ever caught a comet this close to its fragmentation event. The delay is a mystery. It is a small mystery by the standards of unsolved problems in astrophysics, but it is a mystery that should not exist according to the models we had before November 8, 2025. And it is a mystery that only became visible because a backup observation program accidentally pointed a telescope at the wrong comet at exactly the right moment. And then there is the chemistry, because K1 is not just interesting for how it broke apart, it is interesting for what it is made of. Ground-based spectroscopic analysis of the comet's outgassing, conducted in parallel with the Hubble observations, revealed something unexpected about K1's composition. The comet is significantly depleted in carbon compared to all other comets that have been studied in comparable detail. Carbon is one of the most abundant elements in the universe. It is a fundamental building block of organic chemistry. It is present in virtually every comet that has been studied spectroscopically in meaningful quantities. The carbon depletion seen in K1 is not subtle and not ambiguous. It is a real chemical signature of an object that formed in a different environment from most of the comets we have studied. This matters because comets are not just interesting as individual objects. They are time capsules. The material inside a comet has been preserved at extremely low temperatures in the outer solar system for 4.5 billion years. It is a sample of the raw material from which the solar system was built, before the processes of planetary formation and geological activity and biological chemistry altered and processed and recycled that material into the worlds we know. When we study cometary composition, we are studying the original ingredients. The carbon and nitrogen and oxygen and hydrogen in a comet are the same carbon and nitrogen and oxygen and hydrogen that were present in the disk of gas and dust around the young sun before a single planet had formed. Understanding what those ingredients were and how they were distributed across the young solar system is one of the fundamental questions in planetary science. Hubble's spectroscopic instruments are still processing the data. The full chemical analysis of K1's fragmentation products has not yet been published. What the team has described as being underway, the detailed spectroscopic characterization of the gas streaming from the freshly exposed interior of the fragmented comet. It may reveal even more about what K1 is made of and what that tells us about where and how it formed. There is something worth sitting with in the story of how this discovery happened. The research team had proposed a dedicated program to catch a comet breaking apart in real time. They had competed for the telescope time. They had failed to get it. So they were not doing the thing they had planned to do. They were doing something routine and secondary, a backup observation of an unremarkable comet chosen not for scientific interest, but for scheduling convenience, and the universe delivered anyway. Bodowitz, the principal investigator, described it directly. Sometimes the best science happens by accident. He is right, but there is something more specific than accident at work here. The reason the accidental discovery happened is that the team was paying attention. They were looking carefully at the data. When Noonan opened the images the morning after the first observation and found 4 comets where there had been one, he recognized immediately that what he was looking at was extraordinary. He did not dismiss it. He did not assume it was an instrument artifact. He followed it. K1 Atlas is in that tradition, a backup target, a team paying attention, 4 comets where there had been one. C/2025 K1 Atlas, the object that formed 4.5 billion years ago in the outer disk of the young solar system, that survived intact through billions of years of orbital evolution, that made its closest approach to the Sun inside the orbit of Mercury, and experienced the most intense solar heating it had ever encountered. That began to break apart 8 days before Hubble pointed at it and continued fragmenting while the telescope watched, is now a collection of pieces. At least 4 fragments, each following its own trajectory, each surrounded by its own diminishing cloud of outgassing material, each heading outward through the solar system away from the Sun. The comet itself is gone now. What remains is the data. The 3 days of Hubble images showing a comet breaking apart in real time for the first time in the telescope's 35-year history. The spectroscopic analysis that revealed a carbon-depleted composition unlike any comet studied before. The mysterious delay between fragmentation and brightening that the standard model did not predict, and that future research will have to account for, and the story of a backup observation program that accidentally delivered one of the most remarkable serendipitous discoveries in the history of solar system science. We were looking at the wrong thing. The universe made sure we were looking anyway. And what we saw in those 3 20-second exposures taken on 3 consecutive November days was something 4.5 billion years old, dying for the first time in front of a camera that was never supposed to be pointing at it. Good night.